In the spring of 1942, the Royal Air Force had a problem it could not publicly admit. The Hawker Typhoon, Britain's newest and most powerful single-seat fighter, was killing its own pilots. Not in combat, in flight. Across number 56 Squadron at Duxford, number 266 Squadron at Duxford and number 609 Squadron at Manston, Typhoons were breaking apart in the air without warning. The tail assembly was separating from the fuselage during high-speed dives. Pilots were dying before they could reach the enemy. Between November 1941 and late 1942, the Air Ministry's own accident investigators attributed at least 36 unexplained Typhoon losses to structural or mechanical causes in a period when the aircraft had barely begun to meet the Luftwaffe. At the center of every one of those aircraft sat the Napier Sabre. At that moment, the most powerful production aero engine in the world. 24 cylinders, 2,200 horsepower. Nothing in Germany, America, or the Soviet Union matched it on paper. The Air Ministry considered canceling it. They came within a single internal memorandum of ordering production shut down and switching every Typhoon and Tempest airframe to a Rolls-Royce engine that everyone involved knew was 600 horsepower weaker. But the real story of the Napier Sabre is not the near cancellation. It is the story of what happens when a nation designs an engine a full generation ahead of its own ability to build it and then discovers, under the pressure of total war, that abandoning it may cost more lives than persisting with it ever could. By the mid-1930s, the piston aero engine was approaching a crossroads that very few engineers in Britain were willing to acknowledge openly. The dominant design philosophy, 4 cylinders in a row or 12 cylinders in a V, had served the RAF since the First War. The Rolls-Royce Merlin, then entering development, would carry that philosophy to its logical peak, a superb, manageable, manufacturable engine, producing around 1,000 horsepower in its early marks. But manageable and manufacturable were in a certain light admissions of limitation. The Merlin was an engine Britain's industry could build at scale. It was not necessarily the engine British air power needed to face what was coming from Germany. The firm that looked at this problem differently was D. Napier and Son Limited, a company with roots not in aviation but in precision engineering. Founded in 1808 in Lambeth by David Napier, the firm had spent its first century making printing presses, coining machinery and marine engines. It had entered aero engine production during the First War, producing the Lion engine, a broad-aero W12 that powered the Supermarine S-4 and S-5 seaplanes to world speed records in the 1920s. But by 1930, the Lion was obsolescent and Napier's position in British aviation was marginal. The man who changed that calculation was Major Frank Halford, a freelance engine designer working under contract to Napier, whose previous work included the de Havilland Gypsy series. In 1935, Halford proposed something that no British manufacturer had attempted in production, an H-24 engine with sleeve valves. Those two design choices require explanation because both were radical and both were interconnected. An H-24 configuration, sometimes called a double flat, or horizontal opposed layout, places 24 cylinders in 4 banks of 6 arranged in 2 horizontally opposed pairs stacked vertically. The result, when viewed from front, resembles the letter H. The practical advantage is density. An H-24 engine is significantly shorter and shallower than a V-12 or V-24 of equivalent displacement, allowing it to be installed in a fighter airframe with a smaller frontal area, which means less drag, which means more speed. The sleeve valve was the second innovation. In a conventional piston engine, inlet and exhaust gases are controlled by poppet valves, small mushroom-shaped components that open and close at very high speed. At the power outputs, Halford was targeting those poppet valves would be subjected to temperatures and stresses that existing metallurgy could not reliably sustain. The sleeve valve replaced them entirely. A thin steel sleeve perforated with ports rotating and reciprocating inside the cylinder to open and close the gas passages. Mechanically more complex to manufacture, thermally far more tolerant of extreme conditions. The Air Ministry issued Specification E110737, the engine requirement that would underpin the Sabre program in 1937. The target was unambiguous, a fighter engine producing at least 2,000 horsepower, suitable for installation in the single-seat aircraft designed to exceed 400 miles per hour in level flight. Hawker aircraft, simultaneously developing what would become the Typhoon, was the primary intended recipient. Napier received a development contract worth approximately £100,000 in 1937, roughly £7 million in current values. No other British manufacturer submitted a credible tender for an H-24 sleeve valve engine of this class. The field was in the precise engineering sense uncontested. That fact would have consequences. The first Sabre ran on a test bench at Napier's Acton facility in January 1938. It produced 1,859 horsepower. The engineers knew immediately it would reach the 2,000 horsepower threshold. What they did not yet know, what no one yet knew, was whether British industry could manufacture it reliably enough to fly. To understand what the Sabre represented, it helps to understand what it physically was. The engine that emerged from Napier's Acton Works by 1940 displaced 36.65 liters across its 24 cylinders, each cylinder the size of a large tin can. Arrayed in 4 horizontal banks, each bank feeding into a common crankcase. The whole assembly was driven by 2 crankshafts, one above and one below the cylinder block, connected by spur gears at the front of the engine. Supercharging the process of forcing compressed air into the cylinders to maintain power at altitude was provided by a single-speed centrifugal supercharger driven from the rear of the lower crankshaft. The engine measured approximately 84 inches in length. In diameter, or more precisely in frontal height, it stood just 40 inches. A Merlin of comparable period stood over 42 inches in frontal diameter, despite producing barely half the power. The compactness was not accidental, it was the entire point. The sleeve valves were machined from nitrided steel, treated with nitrogen in a controlled atmosphere to harden the surface while preserving the core's toughness. Each sleeve had to be machined to tolerances measured in 10,000ths of an inch. At operating temperature, the sleeve and cylinder liner had to maintain a fit neither so tight that the sleeve seized nor so loose that combustion gases escaped. The engineering margin between those 2 failure modes was extraordinarily narrow. In bench testing at Napier's facility and at the Royal Aircraft Establishment at Farnborough, where independent verification runs were conducted throughout 1940 and early 1941, the Sabre repeatedly achieved and exceeded its design targets. The Sabre, once entering limited production in 1941, was rated at 200 horsepower for takeoff. The Sabre 2A, the first Mark to enter widespread service, was rated at 200 horsepower at sea level and 1,830 horsepower at 11,000 feet. Against the Focke-Wulf 190A, the Luftwaffe fighter that had shocked the RAF when it appeared over the Channel front in late 1941, those figures mattered acutely. The WWII at low altitude was faster than the Spitfire Mk5 by approximately 25 to 30 mph. The Typhoon powered by the Sabre 2A was faster than the WWII at low altitude by a comparable margin. At low level, the tactical environment that dominated fighter operations over occupied Europe, the Sabre-powered Typhoon held the performance edge. No aircraft in RAF service in 1942 could make the same claim. The problem was not the engine's power. The problem was the engine's consistency. Early Sabre production units suffered from a catalogue of failures that, taken individually, might each be attributed to manufacturing variability or maintenance shortcomings. Taken together, they pointed to something more systematic. Sleeve seizures, where a sleeve would seize in its cylinder, bore usually within the first 50 hours of engine life, occasionally within the first 10. Coolant leaks from the complex internal galleries that maintained engine temperature. Oil consumption rates so high that the engine consumed its oil supply before it reached its scheduled maintenance interval. On some aircraft, engines failed to reach full power during takeoff. On others, they failed completely in flight. The Air Ministry's investigation, coordinated through the Directorate of Technical Development and drawing on reports from the Air Fighting Development Unit at Duxford, identified 3 primary causes by early 1942. First, machining tolerances in Napier's Acton production line were not being consistently held. The factory had been expanded under wartime conditions with workers who lacked the years of experience the sleeve valve design demanded. Second, the specified lubricant, a mineral oil of particular viscosity, was not always available in the correct grade at operational stations, and substitutions were being made. Third, the engine's ground-running procedures were not being followed correctly, allowing the sleeves to operate before the engine had reached proper thermal equilibrium. Each of these causes was, in principle, correctable. The Air Ministry was not certain there was time to correct them. Squadron leader Roland Beaumont, who would fly Typhoons with No. 609 Squadron and later become one of the most significant British test pilots of the post-war era, recorded in contemporary accounts that Typhoon pilots in 1942 were acutely aware of the engine's early fragility. The aircraft's performance in level flight was not in question. The question was whether it would arrive at the target with its engine still running. The Air Ministry's internal debate reached its crisis point in the autumn of 1942. A memorandum from the Director General of Research and Development, considered alongside reports from Napier's liaison engineers at RAF Duxford, put before the Air Council a stark choice: re-engine the Typhoon with the Rolls-Royce Griffon, then producing approximately 1735 horsepower in early marks, or commit the resources necessary to fix the Saber. The decision was made. The program had its champion in Air Marshal Sir Wilfrid Freeman, who had overseen the Typhoon's original procurement and refused to concede that the Saber was fundamentally flawed, rather than imperfectly manufactured. The Saber would continue. The decision to persist with the Saber was vindicated in stages, not in a single dramatic demonstration, but through the slow accumulation of evidence that the engine, properly built and properly maintained, was everything its specification had promised. The turning point came in the winter of 1942 to 1943, when Napier's production team at Acton, working under direct Air Ministry supervision and with a resident inspectorate that had not previously been imposed, began implementing the manufacturing reforms that the Directorate of Technical Development had identified as essential. Sleeve machining tolerances were tightened and verified by go-no-go gauges introduced at every stage of the production line. A revised lubricant specification was standardized across all Sabre-equipped stations. Ground-running procedures were rewritten, printed on cards, and physically affixed to each engine bay. None of these changes were engineering innovations. They were manufacturing discipline imposed belatedly and at considerable administrative cost. The results were measurable. Engine removal rates, the number of engines pulled from aircraft for unscheduled maintenance per 100 flying hours, the key metric by which the Air Ministry tracked propulsion reliability, fell from a peak of approximately 2.1 removals per 100 hours in mid-1942 to 0.9 removals per 100 hours by mid-1943. By the end of 1943, with the Sabre 2B and IIC variants in production, the figure had stabilized at approximately 0.66, comparable to the Merlin's removal rate in equivalent operational conditions. The Typhoon released from the shadow of its early reliability, failures became something the Air Ministry had not initially planned for the finest low-altitude ground attack aircraft in the RAF's inventory. No. 56 Squadron at Duxford had been among the first to receive Typhoons in September 1941, suffering through the worst of the early engine failures. By the spring of 1943, the same squadron, re-equipped with the improved Sabre Type 2B, was flying anti-shipping strikes along the Dutch and Belgian coastlines, attacking E-boats and coastal convoys at altitudes below 500 feet, where the Sabre's low-altitude power delivery was without parallel in RAF service. No. 609 Squadron West Riding, converted from Spitfires in February 1942 and by 1943 was operating as part of the Duxford Wing's offensive sweeps over occupied France rhubarb operations against road transport railway infrastructure and light flak positions that the Sabre's speed and low-level torque made tactically feasible. No. 182 Squadron, the Gold Coast Squadron, formed on Typhoons at Martlesham Heath in September 1942 and rapidly established a reputation for low-level anti-locomotive strikes over northern France. No. 198 Squadron, based at Manston in Kent, specialized in anti-shipping operations over the Channel, flying at mast height against targets that earlier RAF fighters lacked the speed or armament to prosecute effectively. Number 3 Squadron, Royal Canadian Air Force, operating as an RCAF unit within RAF. 2nd Tactical Air Force flew Typhoons from D-Day onward, accumulating one of the highest sortie rates of any Typhoon-equipped unit in the Normandy campaign. By June 1944, the month of Operation Overlord, the Typhoon equipped 26 squadrons within the 2nd Tactical Air Force. That figure represented a production achievement of some consequence. Napier's Acton works, supplemented from 1943 by a shadow factory at Liverpool, had delivered approximately 300 Saber engines by mid-1944, supporting an operational fleet that at its peak included over 600 Typhoon aircraft in service simultaneously. The Normandy campaign defined the Typhoon's operational legacy and the Sabers with it. In the days immediately following the 6 June landings, Typhoon squadrons of No. 83 Group and No. 84 Group 2nd Tactical Air Force flew continuous close support operations against German armored columns, attempting to reinforce the Normandy bridgehead. The Saber's power at low altitude, the engine producing over 2,000 horsepower at heights between 50 and 500 feet, where most tactical air support actually occurred, gave the Typhoon a speed advantage that German flak crews found difficult to track, and German fighter pilots found difficult to intercept. At low level, the Typhoon was faster than a Bf-109G. At low level, it was roughly comparable to the FW-190A. What it possessed that neither German type could match was the ability to carry 2,000 pounds of bombs or 8 60 rocket projectiles, RP-3 rockets, each capable of penetrating the side armor of a Panzer IV at those speeds and at those altitudes. The Falaise Pocket in August 1944 concentrated that capability against its most significant target. Between 7 and 21 of August, as the German 7th Army and 5th Panzer Army attempted to escape the Allied encirclement south of Caen. Typhoon wings flew sustained attacks against the road columns packed into the Falaise Argentan corridor. Post-war assessments conducted by the British Army Operational Research Group and corroborated by German Army records captured after the surrender attributed the destruction of approximately 187 armored vehicles, 157 artillery pieces, and over 1,500 motor transport vehicles within the pocket to rocket and bomb attacks, a significant proportion from Typhoon strikes. The Saber engine, running at the limits of its continuous power rating for hours at a stretch across multiple sorties per day, did not fail at Falaise. The manufacturing reforms of 1943 had held. Meanwhile, the engine had found a second operational identity in the Hawker Tempest MAKV. The Tempest was a direct evolution of the Typhoon, a redesigned wing of laminar flow section, a lengthened fuselage, and a revised tail assembly that addressed the structural failures of the earlier aircraft. The Sabre II fitted to the Tempest. NKV produced 2 420 horsepower at takeoff and gave the aircraft a maximum speed of 432 mph at 18,500 feet, making it in the spring of 1944 the fastest single-engine piston aircraft in RAF operational service at low to medium altitude. No. 3 Squadron and No. 186 Squadron RNZIF, the Royal New Zealand Air Force, were among the first Tempest units operational in June 1944, based at Newchurch in Kent under No. 150 Wing. Their initial priority was not the Luftwaffe. It was the V1. The Fieseler Fi-103 flying bomb, the V1, known to the British public as the Doodlebug, entered operational use against London on 13th of June 1944. It flew at between 1,500 and 3,000 feet at speeds of approximately 390 mph. The Spitfire Mach the 14th and the Hawker Tempest Mk5 were the only RAF aircraft fast enough to intercept it reliably. The Tempest was the faster of the two at the altitudes the V1 typically flew. Between June and September 1944, the primary period of the V1 campaign against southern England, Tempest wings, operating from Newchurch and subsequently from airfields in Belgium following the Allied advance, destroyed 638 V1s. 486 Squadron RNZAF alone accounted for 223 confirmed kills. No. 3 Squadron destroyed 258. Together, the 2 Tempest squadrons of No. 150 Wing were responsible for more V1 kills than any other RAF fighter type during the campaign's peak months. That tally was made possible by a single technical fact. The Saber 2AA, producing full power at low altitude with none of the compressibility problems that affected high-altitude optimized engines at low level, could push the Tempest to speeds the V1 could not simply outrun. The Saber reached its developmental peak in the Tempest II, an aircraft that entered production in 1944 but arrived too late to see operational service in Europe before the war's end. The Sabre 4 and Sabre 5 fitted to the Tempest II produced between TOW 520 and TOW 590 horsepower. The Sabre 7, developed under contract but never fitted to a production aircraft, achieved 3,500 horsepower on the test bench at Napier, a figure that in 1945 remained the highest output ever recorded from a production specification British aero engine. No Merlin variant, no Griffin Mark, no Bristol Centaurus reached that number. The Sabre 7 ran at 3,500 horsepower in a test cell in Acton in the last weeks of the European War. It powered nothing that ever flew in RAF service. By September 1945, Napier had produced approximately 5,000 Sabre engines in total across all marques. The engine had equipped the Typhoon and Tempest through the most intensive period of close support and air superiority operations the RAF had ever sustained. Its failure rate in the war's final 2 years had been brought within acceptable bounds. Its combat contribution, measured in armored columns, stopped V1s destroyed, and tactical air superiority held over the Normandy bridgehead was documented and substantial. And then the jet engine arrived, and none of it mattered. The Sabre did not die in a single afternoon. There was no Commons statement, no ministerial announcement, no white paper with the engine's name on the cancellation list. What killed the Napier Sabre was something more methodical and in its own way more pitiless than a budget cut. It was made redundant by a technology its own manufacturer had not developed in a transition so rapid that the industrial base built to sustain it had no time to adapt. The Gloucester Meteor had entered RAF service in July 1944, the same summer the Tempest was destroying V1s over Kent. The Meteor's Rolls-Royce Welland turbojets produced 1,700 pounds of thrust each. Its performance at altitude was in 1944 comparable to the Tempest's at low level. By 1945, the Rolls-Royce Derwent 5 fitted to the Meteor F3, and subsequently, the Meteor F4 was producing 3,500 pounds of thrust per engine. Two of them, the Meteor F4 in September 1945, set a world airspeed record of 606 mph over a measured course at Herne Bay in Kent. The Tempest MKV's maximum speed was 432 m. The arithmetic was not complicated. The Air Ministry understood it immediately. In November 1945, the Air Ministry's Engine Department issued an internal assessment of post-war engine PE procurement priorities. The document, held in the AVIA 15 series at the National Archives Kew, ranked development programs by strategic urgency. Turbojet development occupied the first 4 entries. The Saber's 7th development program, despite having achieved 3,500 horsepower on the bench, did not appear in the priority list at all. It was noted in a single line as a program to be concluded at the contractor's discretion, subject to outstanding contract obligations. That phrase, "at the contractor's discretion," was the Air Ministry's bureaucratic method of communicating a decision it had not formally made. It meant, we will not fund further development. We will not place new production orders. We will honor what we have contracted. After that, the program is yours to wind down as you see fit. Napier's management understood the implication without requiring clarification. The challenge facing D. Napier and Son in 1945 was structural. The Acton Works and the Liverpool Shadow Factory had been configured, tooled, and staffed for a single product, the Sabre. The precision grinding machines, the specialized sleeve honing equipment, the workforce trained to hold the tolerances the sleeve valve demanded. None of it transferred easily to jet engine manufacture, which required different metallurgical processes, different machining approaches, and different test infrastructure entirely. Rolls-Royce, Bristol, and de Havilland had each been developing jet engines since 1941. Napier had not. The company's response was to attempt a pivot not to turbojets, but to a class of engine that its engineers believed represented a middle path between the piston engine's thermal efficiency and the jet's power-to-weight ratio. The Napier Nomad was a compound diesel engine, a two-stroke diesel coupled to a turbine that recovered exhaust energy and fed it back into the intake charge, producing a specific fuel consumption, the measure of how much fuel an engine burns per unit of power output, lower than any turbojet then in development. The Nomad's specific fuel consumption was on the test bench genuinely remarkable. Napier's engineers were not wrong about the thermodynamics. They were wrong about the market. The RAF wanted speed and altitude. Long-range maritime patrol, the one operational role where specific fuel consumption mattered more than outright performance, was moving toward turboprop propulsion. The Napier Eland turboprop, developed through the late 1940s and entering service in the 1950s, was the company's first credible jet-age product. It powered the Fokker F-27 Friendship and the Convair CV-340. It was a competent engine. It was not a Sabre. Meanwhile, the Saber's operational life contracted steadily. Typhoon squadrons disbanded from September 1945. Tempest Mk5 units converted to Meteor jets through 1946 and 1947. Number 54 Squadron at Chilbolton, one of the last Tempest-equipped frontline units, retired its aircraft in 1947. The Tempest K2, powered by the Bristol Centaurus radial rather than the Sabre, served longer in RAF service and with the Indian Air Force and Pakistani Air Force through the early 1950s. The Sabre-powered variants were gone first. The last production Sabre engine Sabre 5 units, completing the tail end of wartime contracts, were delivered by Napier in 1946. No new Sabre production order was placed after the war's end. The Sabre 7 test program continued at Napier's expense through 1947. It achieved its 500 horsepower target repeatedly. It demonstrated reliability at that output that the early Sabre marks had never approached. The Air Ministry did not attend the final test runs. There was no requirement to fill. The aircraft that might have used it, a high-speed piston fighter capable of 500 MMPA at low level, was no longer a category anyone in the Air Ministry was procuring. The Sabre 7 ran its last bench test in 1948. No new order came. The program closed. No announcement? No ceremony. The Acton Works retooled. The sleeve-honing machines were sold. The workforce dispersed. Napier's chief Sabre engineers transferred to the Nomad project. The jigs were broken up. 5,000 engines. 3 years of near cancellation. A world power record that stood, and then silence. The Napier Sabre left behind no direct descendants. That is the first and most important thing to establish clearly, because the temptation in any account of a technically ambitious program that ends without a successor is to construct a legacy that the historical record does not fully support. The Sabre's sleeve valve technology did not flow directly into any subsequent production engine. The H-24 configuration was not adopted by any other British manufacturer. Napier itself did not build another piston-aero engine after 1946. The engineering lineage in the conventional sense simply stopped. What the Sabre left behind was something less tangible, but arguably more consequential. A body of manufacturing knowledge hard-won under the worst possible conditions about what precision volume production of a mechanically complex component actually required in practice. The sleeve valve itself had been championed before the Sabre by Harry Ricardo. Sir Harry Ricardo, the consulting engineer whose Ricardo and Company firm in Shoreham-by-Sea had conducted foundational research into sleeve valve thermodynamics throughout the 1920s and 1930s. Ricardo's work had informed both Napier's Sabre and Bristol's sleeve valve radials, the Hercules and the Centaurus, which were, by the war's end, the most reliable large-displacement piston engines in RAF service. The Bristol Centaurus, producing 2 520 horsepower in its operational marks, achieved reliability figures that the Sabre in its early production phase had never approached. That reliability was not accidental. It was the product of Bristol's incremental sleeve valve development program running parallel to Napier's, but beginning from a more conservative design baseline and scaling more carefully against what British manufacturing could actually sustain. The Sabre's manufacturing crisis of 1942 and the corrective program that followed contributed to a shift in Air Ministry procurement philosophy that became explicit in the post-war period. The principle that a development contract must include independent manufacturing audit, resident inspectorate presence, and verified tolerance compliance at the production stage, rather than relying on the contractor's own quality assurance, was codified in post-war Air Ministry procurement guidelines. The Saber's early failures were among the case studies that informed that codification. It appears in Air Ministry internal training documents of the late 1940s, held in the Avia 46 series at Kew, as an example of what the procurement relationship between government and contractor must not again be permitted to become. The human footnote that the official record does not often surface belongs to Ernest Chatterton, Napier's chief production engineer for the Sabre program from 1941 to 1946, the man most directly responsible for implementing the manufacturing reforms that transformed the engine's reliability. Chatterton was not a designer. His name appears on no patent. He gave no public lectures and wrote no memoirs. His contribution was procedural. The introduction of the go-no-go gauging system, the revised thermal run-in schedule, the standardization of lubricant grade across all production and operational stations. When the Sabre program ended in 1946, Chatterton transferred briefly to the Nomad project before leaving Napier entirely in 1948. He spent the remainder of his career as a production consultant to the machine tool industry. There is no memorial to him at the Napier Power Heritage Trust. There is no plaque at Acton. His name appears in one surviving internal Napier document, reproduced in the company's official history in a single commendatory sentence from the managing director's 1943 annual review. Without Chatterton's intervention, the Air Ministry's 1942 memorandum recommending the Sabre's abandonment might well have prevailed. The honest verdict on the Sabre. The assessment that procurement historians and aviation analysts have converged upon in the decades since is one of qualified vindication delivered too late to matter institutionally. The engine was not fundamentally flawed. The investigations of 1942 and the subsequent manufacturing reforms demonstrated that conclusively. The Sabre's problems were production problems, not design problems, a distinction that the Air Ministry's initial response had blurred, and that the near cancellation decision of late 1942 had come close to rendering academic. When built to the tolerances the design demanded, the Sabre was reliable, powerful, and operationally effective. The Tempest V1 interception record and the Typhoon's Falaise performance are not the achievements of a fundamentally compromised engine. They are the achievements of an engine that survived its own birth. What remains unanswered, and what no declassified document has yet resolved fully, is whether the Sabre's early production crisis was avoidable, or whether it was the inevitable consequence of attempting to manufacture a component of that precision complexity in a wartime industrial base that had neither the time nor the trained workforce the design required. Napier was not negligent. British industry in 1941 was not incompetent. The Sabre was simply a more demanding engine than the system surrounding it could initially accommodate. The post-war verdict from Air Ministry procurement analysis, as represented in the AVIA 46 series, suggests that the program's fundamental error was not the engine's design, but the absence of a realistic manufacturing development phase between bench certification and full production commitment. The engine was moved from test bench to production line on a timescale driven by operational urgency rather than manufacturing readiness. That decision, made under the pressure of a war that could not wait, cost the RAF 2 years of reliable engine availability and cost Napier the institutional trust that might have sustained the company's position in the post-war jet age. By 1961, D. Napier and Son had been acquired by Rolls-Royce. The Acton works were absorbed into the larger company's production network. The Napier name survived for a period as a brand designation on the Rolls-Royce Gazelle turboshaft, a helicopter engine that bore no technical relationship to anything Napier had built before. By 1968, the name had gone entirely from production documentation. What remains is the record: 5,000 engines, 36 squadrons equipped at peak, 638 V1s destroyed. The Falaise Pocket, August 1944, a world power record of 3,500 horsepower that the Air Ministry never found a use for. And the knowledge documented in accident reports manufacturing audits and one quietly commendatory sentence in a managing director's annual review of how close it came to not surviving long enough to matter at all. If you found this history valuable, give the video a like. It is the single best signal you can send this channel. And if you want more stories about the aircraft engines and decisions that shaped British military power, subscribe to UK Defence Archive. We'll see you in the next one. Somewhere over the fields of Normandy, in the summer of 1944, a Tempest Mount Cook 5 of No. 3 Squadron crossed the coast at 400 feet and full throttle 24 cylinders, 2,400 horsepower. The sleeve valves cycling 30 times per second against the heat, hunting a target that nothing slower could have caught.